Pas disponible aujourd'hui, donc c'est moi qui vais faire ton introduction. Donc bonjour à tous pour le premier midi-map de l'année 2022, présenté par le cartel. Avant de commencer à introduire notre conférencier d'aujourd'hui, je vais commencer par dire que le midi-map suivant sera le mercredi 16 mars, et puis ce sera Marie Dumont, qui est la directrice du Centre d'études de la neige en France, qui nous fera une présentation en lien avec la neige et la télédétection. Donc aujourd'hui, on reçoit le docteur Yassine Brahim, qui est géoscientifique du climat et de l'environnement. Il est professeur adjoint à l'Institut international de recherche sur l'eau de l'Université polytechnique Mohamed VI au Maroc. Et il est présentement en échange, en visite avec Matthew Peros, qui est un des professeurs du cartel à l'Université Bishops. Donc aujourd'hui, Yassine, il va nous parler de la variabilité hydroclimatique en Afrique du Nord-Ouest, qu'il étudie avec les spéléothèmes. Donc Yassine, je te laisse la parole. Tu vas faire ta présentation en anglais, si je ne me trompe pas, et puis tu seras en mesure de répondre aux questions en français après, s'il y a des questions en français. Tiens, ton micro est coupé, juste à l'activer. C'est toujours coupé.
Ah, ok, maintenant?
Ouais, c'est bon.
Ok, parfait. Parfait, merci. Est-ce que vous arrivez à voir mon écran?
Ouais, c'est parfait.
Ah, parfait, okay. So, hello, thank you very much for inviting me to participate in this series of conferences organized by the Centre d'application et de recherche en télédétection of the University of Sherbrooke. The research topic that I will present today is titled The Spéléothèmes Records of Hydroclimate, Variability in Northwest Africa on Multiple Timescales with Potential Implications on Prehistoric Modern Human Populations. So I will start my presentation with a short introduction to paléoclimatology. And then I will try to explain why I'm interested in using spéléothèmes as climate in environmental archives. And I will talk a little bit about my motivation for Northwest Africa as a study area. And afterwards, I will move to the scientific part of this talk, where I will present the published work, the work that we published concerning spéléothème records that cover the last 1,000 years, and the Holocene, the last 12,000 years, and then my ongoing projects that cover longer, older time periods, being the last glacial cycle for the last 125,000 years, and the Middle Pleistocene, which concerns, for my case, the last 500,000 years. So paléoclimatology is defined as the study of the climate history of Earth. This science uses different natural archives from which we can extract proxy data. We can extract data that could be proxies for past environmental and climate changes. And this helps us to understand the climate of the Earth in the past and how it can relate to the present and to future climates. So it can be a baseline for what's going on now in terms of climate change and what can we expect in the future. That's why in paléoclimatology is important. So paleoclimate research uses different climate proxies, which can be either geological or biological evidence preserved in different climate archives, such as sediments, rocks, tree rings, corals, ice sheets, and etc. These archives contain the climate proxies, which are either physical, chemical, or biological. And they can provide information on the past climate and environment, such as the sea level, air and ocean temperature, atmospheric composition, and precipitation. And for most proxies, for using different natural archives, climate archives, the way it works is that we use statistical techniques to define a relationship between the proxy that is measured and the concurrent instrumental record. So basically, the relationship is used to reconstruct the past climate from the proxy data using a calibration or a validation. So the steps that are involved are basically the same everywhere. First, we collect the proxy data and we date the proxy data in the material. We need to do some to know the age of what we are the material that we are working with, which is, for my case, when I say material, for my case, it's spéléothèmes, but for other paléoclimatologies, it can be lake sediments or ocean sediments or tree rings. And then where there is calibration and validation, and then we can proceed to the reconstruction. And each climate archive has its advantages and limits. However, spéléothèmes, the reason I like spéléothèmes, or the advantage of spéléothèmes, is that they are not only rich, especially stalagmites, they are not only rich of paleoclimate information thanks to their stratigraphy and the possibility in their chemical and isotopic composition, which can reflect environmental and climate conditions outside the cave, but also the possibility of doing uranium thorium dating. We can do like the age dating with uranium thorium is absolute. We are talking about absolute dating in high precision dating. So compared to other climate archives, this is an advantage, but there is also the geographic representation, like karsts or caves can be found in many areas around the world. So spéléothèmes samples can be found in many areas compared to ice cores, for example, which are not available everywhere, or in the accessibility to spéléothèmes is generally easier compared to ocean sediments cores, for example. So this is just me talking about the advantage of spéléothèmes, but of course there are also limits, and each climate archive has its limits and advantages. And the commonly used proxies, the proxies that we measure in spéléothèmes, the most common ones are the stable isotopes, being the oxygen 18 and the carbon 13, but there are also trace elements such as magnesium and strontium. We can also measure oxygen 17 excess, which is being developed recently, and there are also fluid inclusions inside the spéléothèmes or the stalagmites, which can be also important for us. Anyway, I can describe these later in other slides. So the way it works, basically the way the hydrological works and how the climate signal is transmitted to the stalagmites is simply because it's part of the hydrological system. So the way the hydrological cycle works is that the water vapor is transmitted from the moisture source, which can be the ocean in this case, towards the continent. Towards the continents, and then the rainfall takes place over the continent, and the rain infiltrates through the soil to join groundwater in aquifers or in caves where spéléothèmes can form. And during this process, the oxygen 18, the oxygen 18 in precipitation and the oxygen 18 in spéléothèmes can have a certain relationship or an equilibrium that can be drawn between them. Once we already have information about oxygen 18 in precipitation outside the cave, and we already know how the oxygen 18 in precipitation, how it relates to temperature, or rainfall amount, rain or snow, or other environmental parameters. Once we understand that, we can extrapolate that relationship to the oxygen 18 in spéléothèmes. In in this way we can actually produce spéléothème records from stalagmites, which actually which actually give us proxies of what happened. Like they can describe what happened in the past in a specific area. And basically, stalagmites are laminated, and each laminae carries information on the environment of different timescales, which can be centuries, decades, annual, and even seasonal resolution, depending on the growth rate of the stalagmite, and also the analytical methods that are being used. And each laminae can be precisely dated using the uranium thorium method. So as I'm showing in the picture on the left, I'm showing an example of the way we extract paleoclimate information for stalagmites. So what we do is that we drill, like what I'm showing here is that we drill along the same layer, the same growth layer. We drill calcite or aragonite powder, depending on the nature of the stalagmite, following the same layer which have the same age. And then we analyze it to know the age of each layer that we choose. And we leave space along the growth axis of the stalagmite, like I'm showing here with the blue dashed line. So the growth axis is, we save it for the proxy that we are measuring. For example, the oxygen 18 or the carbon 13 or the trace elements are being measured across the growth axis. In each drilling point across the growth axis, or even each layer that we date, has a depth value. The depth value is measured with the top of the stalagmite or the bottom of the stalagmite as a reference. And then with this depth value, we can attribute an age to each proxy that we measure, and then we can construct our age depth model. Then we can construct our age depth model, and we can have a time series. So that's how paleoclimate reconstruction from stalagmites work. Now I'm going to talk about why I'm motivated to work in Northwest Africa. So in this region, the hydroclimate variability nowadays is mainly modulated by the North-Atlantic oscillation, which drives the westerly winds belt towards the Western Mediterranean in general in Northwest Africa during the winter season. The North Atlantic oscillation, the NEO, is defined as the pressure difference between the Icelandic low and the Azores high. So when the difference in pressure between the high and the low is large, the NEO is in its positive phase. We call it a positive phase of the NEO. This is when strong winds cross the North Atlantic, bringing wet winter storms from the eastern North America to Northern Europe. When the difference is small, that's when the NEO is in its negative phase. And in this case, the eastern North America and Northern Europe have dry winters with fewer winter storms, but the weather is rainy in Southern Europe and North Africa. So basically, in my study area, it's during negative phases of the North Atlantic oscillation that we receive more moisture, more rain during the winter season. As we show in this correlation map between rainfall and the NEO index during the winter season, the patterns actually resemble the negative NEO conditions. So we confirm that enhanced precipitation over the Western Mediterranean in North Africa is due to a southward shift of the westerly winds belt. However, the summer ITCZ, the summer intertropical convergence zone, is actually located farther south. So there is no summer precipitation in Northwest Africa. We can see that here too, where like in this map, like 80% of the total annual rainfall occurs during the winter season, with the northern areas being more sensitive to the NEO. Here I show the DGF, December, January, February. So this is the winter. So and during summer, the rainfall amount is not significant compared to the winter, and the north of Morocco receives more rainfall compared to the south. And This results in completely different environmental settings between the Mediterranean areas of North Morocco, which are characterized by humid climate and enhanced vegetation, and the arid areas of the Sahara and the Sahara Desert in the south. However, there is plenty of evidence that even the Sahara in the south, even the Sahara Desert, received large amount of rainfall in the past during what's called Green Sahara periods, which we will discuss later in this presentation. Another motivation to work in North Africa is the abundance of carbonate formations and therefore the opportunity to use spéléothèmes, which has not been done until the last few years. And even the work that we have been doing in this region is still limited to the Holocene. So for this purpose, we have been conducting several field campaigns to explore new caves, especially those that are not documented yet in the south of Morocco, and to find out whether they have spéléothèmes. And we also acquired a nice collection of samples, either spéléothèmes or water samples from inside the caves, drip water samples, rainwater samples outside the caves. And we visited different caves in the north and in the south of Morocco to have different environmental settings, to have information from both environmental settings. So, one of them, as a geoscientist, one of the main components of my work is the field work. As I said, the most important tasks are the geological characterization of the cave or the karst area that I'm interested in, the sampling of spéléothèmes, stalagmites especially, or water samples, the monitoring inside the cave. As I show here in these pictures, we use some equipment to measure continuously inside caves temperature, relative humidity, drip rate, and CO2 and other parameters as well. And here I show how we collect water samples inside the cave, and we do the same thing outside the cave as well to collect rainwater using appropriate equipment. So this is for the monitoring part, in the fieldwork part, sorry. And regarding the analytical component of my work, the main experimental tasks that we do in spéléothème research include the age dating, mainly using I use the uranium-thorium series, but other methods can be used, such as carbon-14 for the young samples. The stalagmite samples that cover the last 50,000 years or so, if I'm not mistaken. And we also adopt a multi-proxy approach. We analyze stable isotopes, trace elements, triple oxygen, and the isotope composition of fluid inclusions in stalagmites. And finally, the monitoring part, which includes the measuring the isotope composition of drip water and rainwater, which brings important information for the interpretation of spéléothème records. Speaking of monitoring, and since the oxygen 18 is the most common proxy that we use in spéléothème paleoclimate research, it's important to study the stable isotopes composition of meteoric water outside the cave before it's transmitted to spéléothèmes. So here, what I show is an example of monitoring results from North Morocco from 2010 to 2012. We show here that the rainfall amount is negatively correlated to the oxygen 18 in rainfall. So this is from one side. On the other hand, we also show that the rainfall amount during the winter is also negatively correlated to the NEO index. This is an important result because such a relationship between the oxygen 18 in precipitation outside the cave with the rainfall amount from one side and the relationship between the rainfall amount and the NEO index can be actually extended to previous time periods from the oxygen 18 from spéléothèmes. As such, the oxygen 18 in precipitation can be a proxy of rainfall amount, whereas the lowest oxygen 18 values can indicate precipitation amounts that are higher and vice versa. And this is just an example of our monitoring work. The monitoring can be extended to large regions, like or focused on just on meteoric waters, as we did in Morocco. We set up different monitoring programs in different areas in Morocco, and just to understand what really controls the spatial and temporal the distribution of isotopes in rainwater in this area. This is important not only for paleoclimate but also for hydrogeology. For example, to define the recharge area of a specific aquifer, it's important to know the oxygen 18 composition of water, of the parent water, in order to define the recharge area, especially the altitude. However, for my case, I was interested in doing this work in order to be able to interpret all paleoclimate records that use oxygen 18, not just spéléothèmes. And for specific caves, the monitoring can also include data loggers that I showed in a picture before to measure different parameters inside the cave. We also calculate moisture, backward moisture trajectory, especially during extreme events, and we analyze isotopes of water samples inside and outside the cave. So this was just for the monitoring part. So back to stalagmites. What I show here is 2 stalagmites from 2 different caves in northern Morocco, which span the last 1,000 years with a high resolution. And here I'm showing the age model from these 2 stalagmites. So as I already mentioned, one of the main advantages of spéléothèmes is the absolute dating using uranium-thorium and the possibility of achieving very low age uncertainties compared to other natural archives. So here, for example, the age depth model has a resolution of less than 10 years of both stalagmites that I just showed. So the final oxygen 18 records have a resolution of less than 10 years as well. And both spéléothème records that I show here in the bottom, the black curves, they show substantial multidecadal to centennial variability. And the interpretation of the oxygen 18 in both records relies on the relationship that I mentioned before between the oxygen 18 and precipitation, the rainfall amount outside the cave, which we retrieved from the monitoring results. As such, periods with low oxygen 18 values indicate wet time periods and vice versa. And we also see a high consistency confirming that both spéléothème records, like the variability, overall variability is similar. When we did the PC1 analysis, we found similar, like a high consistency, like statistical significance. So we decided to make a composite record that is representative of the climate change of the climate variability of the last 1,000 years in northern Morocco. So here we compare our spéléothème record, our composite spéléothème record, with the NEO, the North Atlantic Oscillation reconstructions for the last 1,000 years. And the comparison shows that to a good extent, the low oxygen the periods of the low oxygen 18 values indeed coincide with negative phases of the North Atlantic Oscillation and vice versa. Which could explain that the relatively dry conditions during the MCA, the period called medieval climate anomaly, from 950 to 350, from the years 950 to 1350, and the opposite, which is the relatively more humid climate conditions in North Africa during the period called the Little Ice Age, from around 1550 to 1850. The same finding is valid through the comparison of our spéléothème records for the last 150 years with the instrumental. So here I'm using the instrumental NEO index, and we can see that to a good extent, the variability is more or less similar. And what's interesting is the well-documented drought tendency that is well documented in Morocco after the 1960s. And we can see that it's also transmitted and that it's also recorded in our spéléothèmes. And from South Morocco, we worked on another sample from Ifrika Cave in the Western High Atlas Mountains, and we followed the same analytical procedure that I described before for the North Morocco. So here I'm showing the South Moroccan, the new South Moroccan record for the last 1,000 years compared to the North Moroccan record that I explained in detail before. So the comparison shows that on the centennial scale, the centennial scale variability is more or less the same between South and North Morocco, with a significant difference around the year 1050, where we can see that there is an antiphase with drier conditions that started the drier conditions of the medieval climate anomaly that started earlier in South Morocco. However, on centennial timescales, the climate variability between South and North Morocco is more or less the same. That's why we decided to do some spectral and wavelet analysis to see the substantial periodicities, climate change periodicities between both from both records. What's interesting is that the periodicities, like we can see that indeed some multidecadal and even centennial periodicities are actually significant. But what's interesting is that the periodicities of about 200 years are actually the most significant. They have the highest power, and they are continuous throughout the entire 1,000 years. These 200-year periodicities in the spectral analysis are well known, are close to a well-known solar cycle called the Vrice-Suez. So just the fact that we have 200-year periodicities that are strong and continuous throughout the entire records, and doesn't necessarily mean that they are attributed to that they are related to some solar forcing. So we have to prove that. We wanted to check if that's true. So what we did is that we compared our records, our spéléothème records, with two solar activity reconstructions, and what we could see is that indeed during the well-known solar minima periods of the last 1,000 years, we can see that they coincide with an increase of precipitation amount in North Africa, especially in the Mediterranean area of North Africa. This is consistent with modeling results as well, which suggest that low solar activity can result in a south shift of the westerly winds belt, which would drive the moisture flow toward Northwest Africa and the Western Mediterranean in general. Finally, across spectral analysis between our spéléothème data in solar activity reconstruction shows that indeed the hydroclimate variability in Northwest Africa is driven by solar forcing, as we can see here. Like around the year 200, we can see with the arrows that this is consistent. And so what we did in this work is that we provided proxy evidence of the climate response of in the Western Mediterranean to centennial scale forcing through NEO-like conditions during the last 1,000 years. And very recently, we used 3 different stalagmites from South Morocco, which actually provide evidence of a rapid drought tendency during the 20th century, which is actually evidence of the transmission of anthropogenic signal to natural climate archives. So this is an example of how the anthropogenic signal can be transmitted to natural archives. What the results that we show in this work is that the dry conditions of the 20th century are actually unprecedented. So they are actually they developed more rapidly than during the medieval climate anomaly, for example. And this is likely due to the rising atmospheric CO2 levels. And actually, this pattern that we see here, actually, it's similar to a pattern called the hockey stick pattern. So this is the hockey stick pattern, which is related to the increasing temperatures due to global warming. So in this work, we demonstrate that the rapid drying in North Africa is actually linked to the warmer sea surface temperatures over the Atlantic Ocean, which are opposite to the sea surface temperatures of the coast of Northwest Africa, which actually are cooler. And this difference of temperature, this difference of sea surface temperature actually intensified the Canary current of the coast of Northwest Africa, which increased the biological productivity in the coastal fishing industry in Northwest Africa. And now, regarding the Holocene, now I'm moving to another time period, the last 12,000 years, the Holocene. We actually extended our work in order to this time period, in order to understand the impact of high latitude North Atlantic abrupt climate events called bond events, which took place during the Holocene. We wanted to know how these high latitude North Atlantic events can affect the climate in Northwest Africa. So that's why we worked on samples from northern Morocco, which is more sensitive region to the North Atlantic oscillation. We also used spéléothèmes from South Morocco to answer another important question about the extent of the African monsoon during the Holocene. So I'm going to talk in detail about that. So basically, what we did is that we constructed a high resolution rainfall index that from our stalagmites in North Morocco, which I'm showing here in the bottom, the black curve. And what we show here is that the North Atlantic ice rafting events, which are numbered here, they coincide with humid periods in the Western Mediterranean during the early Holocene and during the late Holocene. However, this is not clearly the case during the mid-Holocene, as we can see from the comparison with the Azores front, which record, which indicates that the Azores front was actually located north during the mid-Holocene, and also a storminess record from Denmark, which shows an increase of storminess, and therefore, which is actually comparable to positive ENO conditions during the mid-Holocene. So basically, the conclusion that we could draw from this work is that the position of the westerly winds belt was actually which was actually negative during the ice rafting events of the early Holocene in the mid-Holocene. This was not the case during the mid-Holocene. So what we could say is that contradictory mechanisms involving probably prolonged periods of both north and south shifts of the westerly winds belt, which resemble positive and negative ENO patterns, might at least partially trigger or amplify the ice rafting events and the slowdown of the Atlantic meridional overturning circulation. And regarding our samples from South Morocco, like on the other hand, what we wanted to do is to answer a question about the extent of the Green Sahara conditions. As many of you know, North Africa hosts the largest hot desert in the world, the Sahara, as well as one of the most prominent monsoon systems, the West African monsoon, which is crucial for millions of people who live in this region. And as I show in these two maps, like I'm showing the Sahara Desert map, like with resembling what's today's conditions compared to Green Sahara. where you can see more vegetation and mega lakes, which is actually related to the extent of the African monsoon that could reach farther regions in the north, and also the position of the ITCZ, which is north compared to today. In order to actually have a clear idea about the extent of the African monsoon during the past, during the Green Sahara periods, we used a spéléothème record from the south of Morocco, which I show here. And it actually indicates an increase, a substantial increase of precipitation from starting about 10,000 years ago and being more persistent between 9 and 4,000 years ago. This period actually in the paléoclimate literature is coincides with a Green Sahara period. And actually what we could draw from this work, since our stalagmite is located on 31 degrees north, we could actually conclude that the North African, the West African summer monsoon fringe could actually reach 31 degrees north during the Holocenes, the most recent Green Sahara period, also known as the African humid period. The comparison with our spéléothème record from North Morocco shows that the African monsoon fringe could not reach 34 degrees north, because we could not see that in our spéléothèmes from the north of Morocco. And this can be explained by the fact that the high Atlas mountains could actually make a topographic barrier that blocks the moisture that is coming from the south from reaching farther north, or simply the fact that the monsoon was actually already weaker and not able to reach farther north. And regarding our work that is in progress concerning older time periods, not just the Holocene or the last 1,000 years, the reason our motivation to continue working in this direction is that the African humid period of the early to mid Holocene is only one among many Green Sahara periods, and these periods are not documented. So our objective is to fill the spatial and temporal gaps in Northwest African paleoclimate literature beyond the Holocene. So our current work in progress is about producing continuous multi-spéléothème climate records of the last glacial cycle. And with this new data, what we want to do is to reveal the exact timing and magnitude of Green Sahara periods, to document and understand the teleconnections between the North Atlantic abrupt climate events and the North African monsoon, and also to test the theories about the climate pacing of human dynamics within Africa and outside of Africa. So now I'm going to show quickly some of the preliminary work that I have been doing. This concerns a multi-proxy record, spéléothème record from South Morocco, which covers a period called MIS5A, the Holocene first, which I already talked about. And now I'm going to talk about this period called MIS5A, which is somewhere between 70 and 90,000 years ago. So the comparison of my data with other paleoclimate records from the Levant, from East Africa, West Africa, indicates a certain consistency, which actually demonstrates that MIS5A is actually indeed a Green Sahara period. What's actually interesting here is that we used 17, like what you can see here as red stars, is data points, a new proxy that is being developed in the spéléothème paleoclimate research is the oxygen 17 XS. What we can see here is that from the values of our 17O XS is that there is a substantial increase of winter precipitation during this Green Sahara period compared to the Green Sahara of the Holocene. And this is an interesting result because it's different from the common assumption that green Sahara periods are the result of an increase of summer precipitation related to the monsoon rather than winter precipitation. Like most common assumptions, do not take winter precipitation into consideration. And what we show here is that actually the winter precipitation during this green Sahara period are more significant than the summer precipitation that we can see during the most recent African humid period. And the comparison of our data, on the other hand, with a human density model reveals an increase of human density, increase of population in this region during MIS 5A, which is confirmed by archaeological evidence that shows that the Assyrian technology, for example, was actually more developed during this period in North Africa. So here we show that these prehistoric human populations were actually sustained by winter precipitation during this green Sahara period. And one of the main conclusions of this work regard the abrupt climate deterioration during the MIS 5, MIS 4 transition. We can see that the climate became drier, and this coincided with a decline of human density in North Africa, and actually no Assyrian sites are dated in the Sahara after this period. Maybe it's because of the lack of dating, but it could also indicate that some climate force dispersals of prehistoric humans who might have migrated to other places, because the Assyrian population continued along the Mediterranean, the Mediterranean part, so the northern part of the southern Mediterranean. In fact, the Assyrian industry is a stone tool tradition found widespread throughout northern Africa during the late Pleistocene. The oldest Assyrian site was dated to 150,000 years ago in Morocco, and the number of Assyrian sites increased at about 130,000 years ago. And however, the onset of the Assyrian industry can be seen as a pulse of innovation, which might have coincided with an amelioration of climate conditions. And the Assyrian industry, we think that it disappeared about 30,000 years ago, and does not appear to have influenced the Ibero-Mauritian culture that appeared in the Maghreb 25,000 years ago after an archaeological hiatus of several thousands of years. So the problem is that it is not clear whether the rise, expansion, and demise of the Assyrian industry in North Africa was related to climate and environmental conditions. And for this, we need more paleoclimate evidence for the region, but we also need to date more Assyrian sites in the Sahara and in other places, such as farther east or farther north towards the Mediterranean areas. For this purpose, we have been working on different stalagmites, which are promising. The preliminary dating is promising, and we can be able to produce a multi-spéléothème, multi-proxy in high-resolution climate records that covers the entire last glacial period, which would be very helpful to achieve our goals. I'm also interested in extending my paleoclimate records in Northwest Africa to previous periods, to the last 500,000 years, to reconstruct the hydrologic and environmental history of North Africa, but also to evaluate the impacts of environmental changes on the anatomically modern humans in North Africa, with an emphasis on population dynamics, refugium networks, and cultural changes that happened during the Middle Stone Age. Actually, it has been shown by the compilation of data, of paleoclimate data, that the Green Sahara periods were closely linked to the history of human populations. However, most of the data, most of the data that can cover the last 8 million years, they suffer from either low resolution, low precision, or the fact that there is not enough geographical coverage of all areas of the African continent. And on the other hand, different human dispersal scenarios out of Africa in theories about the origin of modern humans, which take environmental conditions into consideration, they do not include Northwest Africa. So Northwest Africa has been one of the most neglected areas, one of the most neglected areas, which actually needs to be put into question and need a particular attention, especially with the oldest modern Homo sapiens remains that were found in Morocco in the date back to about 300,000 years ago. And from the same region, we don't have any paleoclimate evidence that dates back to before and after this period, which can be important to see whether the oldest known modern Homo sapiens, whether they were living within refugium as isolated or semi-isolated populations in North Africa, or whether with the coupling of paleoclimate data with archaeological and genetic evidence can give us insight about whether those oldest known modern humans were archaic populations that lived isolated, or whether the environmental conditions would have allowed them to have more continuity and whether they could actually expand their genetic flow within Africa or maybe even outside of Africa. And thank you.
Merci beaucoup, Yassine. La présentation était extrêmement intéressante.
Si.
Est-ce que des gens ont des questions pour Yassine? Oui, Noura, pardon.
Je peux pas vous entendre. I can't hear you.
Can you hear me now?
Yes, can you speak up, please?
Yes. Hello, Yassine. Thank you for this amazing presentation. I have a small question about what do you prefer, stalagmite rather than stalactite in your
okay, that's
the analysis.
Okay, so actually stalagmites, the reason I prefer to use stalagmites is because you can see here, as I explained before, is that the proxies that we measure in stalagmites, such as oxygen 18 or carbon 13 or trace elements, we actually extract them, we drill them across along the growth axis of the stalagmite. In the case of stalactites actually are the ones that feed the stalagmites, right? So actually the growth axis, like the center, that's where the drip wire is traveling along. So it's simply easier. It's easier to just use stalagmites. And in my case, from my experience, I tried to work with stalactites, but I couldn't see the same stratigraphy. I couldn't see the layers easily. And even like I said, I don't really trust the growth axis of the stalactites because that's where the drip wire is traveling from. So, and I prefer to mix, in order to make sure that what I'm measuring has an equilibrium from one layer to another, it's important to follow the growth axis. Otherwise, it's possible to use stalactites, but it's simply more difficult.
Okay, I can see. I have another question, if you permit me to ask it.
Oui, vas-y.
Thank you. Just in your perspective research, you say that you choose 500,000 years as an age limited. Can you give me a reason?
500. Can you repeat the question?
In your perspective research, work in progress.
Okay.
You say that you have chosen for geological. I don't remember exactly.
Yeah, why I choose to work on 500,000 years.
Exactly.
I actually for two reasons. One of them is that the preliminary data that I have, like the samples, I'm showing here two different samples, but I have others. The samples that I have, the oldest samples, they cover maximum of 500,000 years. That's what I could find, like the samples that I could find. But this is and I'm interested in this time period. Like if I can actually produce a time a time series that describes the climate variability in North Africa for the last 5,000 years, then I could actually include some of the archaeological evidence. I could try to couple the archaeological with paleoclimate evidence, which is interesting for me for this time period. As I said, the oldest modern Homo sapiens were found in Morocco in the date to 300,000 years ago. So it would be nice to have a perspective, the climate, to have an overview of climate change before and after the period that we know, that we are sure that Homo sapiens existed, were present in this area during this period. So this is from one hand. From the other hand, the reason for 500,000 years is the precision of the uranium-thorium dating. I'm using uranium-thorium dating, and as I said, each technique has limits and advantages. Uranium-thorium dating is absolute; it's more precise than other methods, but it also has a limit of 500. Like once you exceed 500,000 years, it becomes less precise. Of course, there are spéléothèmes. We can find, I wasn't lucky to find spéléothèmes that date to 1 million years or more, but there are spéléothèmes that are older than 500,000 years. But in that case, we need another dating method, like uranium, lead, uranium, plump.
Okay.
Yeah.
Okay, thank you so much, Yassine, for this presentation.
Thank you.
Est-ce qu'il y a d'autres questions? Dans ce cas, moi, j'en aurais une pour toi.
Oui.
Quelle va être la différence parce que là, il y avait beaucoup de travail qui était déjà fait sur le premier millier d'années ou jusqu'au début de l'Holocène, puis là, tu t'attaques à genre 500 000 ans. Ça va être quoi la différence de résolution temporelle entre ce que tu vas réussir à dater sur les premiers 10 000 ans ou les premiers milliers d'années, où je crois que tu avais une résolution temporelle d'environ 10 ans, si j'ai bien compris.
Ouais.
Et puis, comme ce sera quoi ta résolution temporelle, mettons si tu arrives à remonter comme à 500 000 ans, est-ce que tu es toujours à 10 ans ou est-ce que tu es plus comme à 500 ans ou est-ce que tu es à...
Alors, pour répondre à votre question, ça dépend. En fait, pour moi, ce qui serait optimal, c'est d'avoir la même bonne résolution de moins de 10 ans sur toute la période. Mais ça va coûter beaucoup d'argent. Parce que quand on parle de 500 000 ans, si je fais 10 ans de résolution, ça va faire 50 000 analyses d'oxygène 18. Déjà, ça prend beaucoup de temps et beaucoup d'argent. En plus, la raison pour laquelle ce qu'on fait pour les derniers 1000 ans, par exemple pour l'Holocène, on essaie d'avoir la plus haute résolution possible parce que c'est important pour la plupart des modèles paléoclimatiques, par exemple. Il inclut dans les bases de données paléoclimatiques, il inclut par exemple les enregistrements isotopiques de haute résolution pour l'Holocène, qui est plus important pour décrire, par exemple, le futur. Mais moi, ce que je fais pour les périodes qui sont un peu plus longues, je m'intéresse plutôt à la variabilité orbitale. Et dans ce cas, les périodicités décadales, la variabilité décadale ne m'intéresse pas trop. C'est juste des bruits dans ce cas. Parce que le fait de reconstruire des pics chaque année, chaque 10 ans, pour une période de 500 000 ans, on ne peut pas les voir de toute façon. Mais ce qu'on fait parfois, c'est par exemple, ce que je peux faire pour les 500 000 ans, c'est de reconstruire une résolution de par siècle ou par 50 ans, au lieu de faire par 10 ans, 50 ou 100 ou 200 ans. Mais je peux aussi améliorer la résolution dans certaines key time periods, des périodes qui sont très importantes.
Ouais.
Oui, juste pour des petites fenêtres dans les 500 000 ans avec une meilleure résolution, mais le reste, pas nécessairement.
Ok. Et puis j'aurais peut-être une couple d'autres questions, sauf s'il y a d'autres personnes qui ont des questions à poser, auquel cas faites juste lever la main. Là. Tu disais que là, toi, dans la région que tu étudies, a priori, le spéléothème que tu as trouvé qui permettrait de remonter le plus loin, ce serait à peu près 500 000 ans.
Oui.
En théorie, tu serais capable de remonter jusqu'à... Du coup, je comprends qu'il y en a d'autres qui permettraient de remonter plus loin ailleurs sur la planète.
Oui.
En théorie, tu serais capable de remonter jusqu'à quelle période de temps?
Avec les spéléothèmes.
Ouais.
Honnêtement, je ne sais pas s'il y a vraiment une limite. Je sais honnêtement, je ne sais pas. Ça dépend vraiment. Dans ce cas, le problème, c'est toujours les datations.
Ouais.
Au-delà de 500 000 ans, comme j'ai dit, ça devient un peu compliqué parce que même avec l'uranium plomb, c'est pas aussi. C'est une méthode qui est en train de s'améliorer. C'est une méthode qu'on est en train de développer encore et encore. Et ça, c'est une science qui est jeune, qui vient de commencer. Donc, il y a toujours des développements et des améliorations. Je sais qu'il y a des enregistrements isotopiques qui ont été publiés et qui dépassent 1 million d'années, mais ils ne sont pas très nombreux. Ils sont pas nombreux.
D'accord. Et par exemple, toi, là, pour remonter à 500 000 ans, genre on parle de quelle taille de stalagmite, par exemple? Ça représente quoi?
La taille, en fait, la taille n'est pas... Parfois, au niveau des stalagmites, le taux de croissance de la stalagmite est différent d'un cas à un autre. Par exemple, ici, je ne sais pas, est-ce que vous voyez, est-ce que vous
Ouais.
Okay.
Ouais.
Par exemple, ici, la stalagmite est de 30 cm seulement. Mais 30 cm seulement, et on voit déjà une variabilité entre 200 000 et 500 000. Mais donc, on a 300 000 ans d'enregistrement dans la même stalagmite, dans 30 cm seulement. Mais par contre, ici, par exemple, à droite, on a une stalagmite qui fait 1 mètre et qui enregistre uniquement l'Holocène, 12 000 ans.
D'accord.
Vous regardez la différence, 12 000 ans dans 1 mètre comparé à 300 000 ans dans 30 cm. C'est large quand même, mais ça ne veut pas dire que, dans l'exemple que j'ai montré ici, ça ne veut pas dire que toutes les 300 000 ans sont enregistrés dans la même stalagmite. Il se peut qu'il y ait des périodes d'interruption.
D'accord, ouais.
Il se peut qu'il y ait des hiatus. C'est pour ça que nous, généralement, on préfère avoir plusieurs stalagmites. Parce que parfois, on a une stalagmite qui va de 9 000 ans à 95 000 ans, mais avec 10 000 ans qui manquent ici. Mais on peut les trouver ici.
Ok, ouais.
C'est pour ça, parce que les eaux de Sointemont, la goutte d'eau qui nourrit la stalagmite, il peut se déplacer. Et il se peut que pendant une période donnée, la stalagmite n'enregistre pas cette période, donc il faut la prendre. Alors vraiment, la taille de la stalagmite ne reflète pas vraiment la durée de temps qu'il enregistre.
Du coup, j'imagine que ça doit être assez difficile quand tu arrives dans une cave et que tu vois des stalagmites, d'estimer, genre d'avoir une estimation de jusqu'à combien tu es capable de remonter. Tu n'as pas le choix d'aller faire des analyses précises pour voir l'information que tu peux aller en tirer, en fait.
Oui, on n'a pas vraiment. Si par exemple, moi, je vise cette période exactement, je n'ai pas vraiment le choix. Je dois prendre des stalagmites et les analyser et voir ce que ça donne. Alors, ce qu'on fait, on fait des datations préliminaires généralement. Par exemple, ici, moi, je m'intéresse par l'Holocène, par exemple. Ce que je vais faire avant de détruire la stalagmite de la grotte, parce que c'est quand même un environnement qu'il ne faut pas détruire, ce qu'on fait, c'est de faire des datations préliminaires. On prend avant de casser la stalagmite, ce qu'on fait, c'est de prendre un échantillon de poudre le bottom, en bas de la stalagmite, à la base de la stalagmite, parce que ça représente généralement la couche la plus ancienne.
Ouais.
Et on prend un autre échantillon de poudre du haut de la stalagmite. Comme ça, on a une idée sur la période de temps que cette stalagmite enregistre. Et une fois au labo, on analyse, on fait les datations, les datations préliminaires. Et une fois on sait que ces stalagmites-là couvrent l'Holocène, on retourne à la grotte pour la casser. Parce que sinon, on a cassé une stalagmite pour rien.
Ouais, c'est sûr.
Ouais.
Super. Bah, écoutez, s'il n'y a pas d'autres questions, je pense qu'on va terminer la période de questions ici. Et que, merci beaucoup Yassine
Merci à vous.
pour ton temps et puis ta présentation. Et puis de nous avoir fait découvrir, pour ceux qui ne connaissaient pas ou pas trop comme moi, l'idée des stalagmites pour la datation du climat comme ça. Et puis j'en profite d'avoir encore quelques personnes de connectées pour dire que notre prochain Midi Map, ce sera donc le 16 mars prochain. Et puis ce sera avec Marie Dumont, la directrice du Centre d'études de la neige, qui nous parlera de télédétection sur la neige. Donc encore merci à tous pour avoir assisté au Midi Map. Et puis merci Yassine.
Merci à vous.
Et à la prochaine.
Ciao.
Salut.